Hi everybody, welcome back to the Feynman technique. Today we'll be taking a look at this integral, another integral I got off the channel Maths 505. The solution process is similar, although I will be going into greater detail about some of the steps and the motivations for taking those steps. Alright, so let's take a look at this integral. The first thing you would probably notice is we have a bunch of x squared plus 1 terms. We have one here, we have one here, and we have one here. Now, the one here is the biggest clue. Whenever you see an x squared plus 1 in the denominator of your integrand, that is a huge clue that we are going to let x equal tangent u. So that's going to imply that dx is equal to secant squared u du. All right. Let's go ahead and copy that in here. So if our x is tangent u, well, infinity is tangent pi over 2, and negative infinity is tangent of negative pi over 2. X is just tangent u. Let's see. X squared plus 1 is tangent squared u plus 1, but that's just secant squared u. Also here, secant squared u. And then let's go ahead, well, let's finish off the substitution. Our dx is secant squared u du. And this x squared plus 1 is, again, secant squared u. All right, this secant squared u is going to cancel the other secant squared u. And this 1 over secant squared u will become cosine squared u. All right, let's simplify this a little bit. We know that the tangent is just sine u over cosine u, and secant squared u is just 1 over cosine squared u. So let's multiply the numerator and denominator of this exponent by cosine squared u. So in the bottom, we'll just be left with this 1, and multiplying by cosine squared u. Let's see, 1 factor of cosine u will cancel out here, and we'll just be left with this. And then I'm going to have to put a parentheses around these to make Desmos read it, and we can get rid of that 1. All right, let's go a little bit further. This, you'll notice, this is almost the double angle identity for sine. All we need is a 2. So to compensate for that 2, let's divide by 2. Now, 2 cosine u sine u is sine of 2u. Great. All right. Well, we can rewrite our cosine squared u. Don't forget, there's an identity for that. It's 1 plus cosine 2u over 2. So we can just write this as 1 plus cosine 2u over 2. All right, so now we're ready for the next step. Let's see. Let's recognize that this is simply going to be the real part of e to the I times this. Right? So we can rewrite our integral I like this. And then we can bring the real part outside the integral. All right, now let's clean this up a little bit. Let's see. Notice that right here, this is just going to be e to the I over 2 times e to the I cosine 2u over 2. And e to the I over 2 is a constant, so we can bring that right out. So let's bring the e to the I over 2 right outside our integral and get rid of that part. And let's bring this upstairs, and then we can just go like this. We'll just put all this together into one exponent. Just like that. All right, now let's make another substitution. Let's bring it back to x by saying x is equal to 2u. We should have used a different variable, but that's not that big a deal. So dx is equal to 2 du. Let's make ourselves a little 2 du by... we'll just put a 2 right here, and then a 1/2 outside. There we go. So we didn't change anything there. All right. Let's copy our integral. Let's see. Our bounds of integration. Well, if x is 2u, then we're going to go to pi. This is going to go to negative pi. This is just going to become x. This is just going to become x. And our 2 du just becomes dx. All right. Great. So, all right, we're getting somewhere. Okay, let's see. What can we do? Well, I think what we're going to do is right now we're just going to use the Taylor series for e to the x. So e to the x is equal to the sum, as n goes from 0 to infinity, of x to the n over n factorial. Well, this implies that this, e to the sine x plus I cosine x over 2, is equal to this sum, except now, instead of x, we have this. Okay, let's see. We can do a little bit better than this. Let's bring this 2 to the n downstairs. So this is going to be 2 to the n times n factorial. Well, don't forget, we can rewrite this. This is just e to the ix. And this becomes e to the inx. All right. Yeah. So we can go ahead and rewrite our integral now. All right. So we replace this with this. And now what can we do? We can switch the integration and summation notations and bring out everything that doesn't have to do with our x terms outside. Let's see. So that's going to be 1 over 2 to the n times n factorial. Well, let's see. So now we just have to evaluate this integral. Let's go ahead and do that. So, this is just going to be e to the inx over in from pi to negative pi. So we'll just go ahead, go like this, and then we will plug in a pi. So we get I pi, or in pi, and then negative in pi. Great. Okay. Yeah, let's see. Let's see, we have a common denominator here, so we can just say that this is minus this. And now look what we have. This almost looks like sine n pi. Let's see, if we had a 2 here, we could multiply upstairs by 2. And let's actually bring it outside. 2 over 2 over n. And now this is the complex exponential representation of sine n pi, right? Yeah. Equals sine n pi. All right, so our integral is now equal to this. All right, let's go ahead and figure out what this is. Let's go ahead and put a parentheses around this. Let's see. Well, you'll notice, let's figure out, this looks like at sine n pi is going to make almost every single one of these terms 0, is it not? Sine 0 is 0. We have to be careful with that one because technically we're also going to get a 0 in the denominator. So we'll have to take a limit with that one. But for sure, if n is equal to 1, sine pi is 0. And then we have times some other constant. And then sine 2 pi is 0. So literally every single one of these terms is going to go to 0 except for the n is equal to 0 term. Let's figure out what the n is equal to 0 term is. All right, so we need to take the limit as n goes to 0 of this. All right, well, that's going to be the limit as n goes to 0 of this times the limit as n goes to 0 of this. Now the limit as n goes to 0 of this is just going to be, what, 1/2, right? So if we take the limit as n goes to 0 of this part, it's definitely going to be 1 over 2 to the 0, that's 1. No, it's just going to be 1. My apologies. That's going to be 1 because 0 factorial is just 1 and 2 to the 0 is 1. So we can ignore that part. All right. Now let's figure out what the limit of sine pi n over n is. Oops. Sine pi n over n. And then multiply that limit by 2. All right. Well, we already know that this is pi, right? Let's go ahead and show it graphically, though. So if we change this to x, we can see that this is approaching pi. You can use L'Hopital's rule on that if you'd like. Take the derivative of the top and you get n cosine pi n over 1. As it goes to 0, you just get, I'm sorry, yeah, you would just get pi. Yeah, so that's pi. All right, so what did we just say? Every single term except the n equals 0 term is just going to be 2 pi. We're going to get 2 pi. This whole thing right here, it's nothing but 2 pi. All right, so 2 pi. Great. Okay, let's see. This 2 cancels this 2. And now we just need to take the real part of this. So this is equal to the real part of, well, it's going to be pi times the real part of cosine 1/2 plus I sine 1/2. All right, so what does that mean? That means I is equal to pi times the cosine of 1/2. And let's verify that. What was our integral? It was this. Yeah. And that is the correct answer. All right, guys, I hope you enjoyed that. I hope you enjoyed that journey, and we will see you next time.